Good morning, good afternoon, good evening, wherever you may be in this part of the world, and welcome to another session of my series of presentations that I've been making on YouTube. This time, the topic is typical interview questions on power transformers to practice for your interview. And this is part one, and basically our focus is on power transformers. My good name is John Kweko Amuotu. I've been a professional electrical engineer for the past 31 years, and I'm based in the United States of America. This content was put together, first of all, based on my experience as a professional electrical engineer for the past 31 years, and also as a power system and power transformer design engineer, and also, have extensive experience in the manufacturing and testing of power transformers, and also the life cycle management of power transformers in terms of asset management and also maintenance of transformers throughout the whole life cycle of its operation. The first question that I basically based on my experience that I put this content together is, how are power transformers classified? That's a typical, very typical question that you might be asked during an interview. And this is how you answer it. Okay, so this slide basically pertains to how to answer that question when they pose that question to you at an interview, right? Okay, so this is how you answer the question. Power transformers are classified based on the voltage. So that is why we have different voltage classes on the high side and on the low voltage side. Then they are also classified based on MVA outputs. So we have a different MVA outputs for different classes and applications of power transformers. They are also classified based on the cooling class. And a typical example of the cooling class is Onan. Onan means that the oil is flowing naturally, and also air is flowing naturally over the radiator. Then ONAF means that the oil is flowing naturally and the air is forced to blow over the radiator, utilizing cooling fans. Then we also have a special application of power transformers. So a typical example is traction transformers that are used in high-speed rail applications. Then we also have arc furnace transformers, basically that utilizes high current. Then we also have converter stations transformers, basically that are used for HVDC transmission application. They are also classified based on the winding configuration, right? Okay, so that is why we have a typical example is delta Y ground. So delta means that the high side is wound in the delta configuration, and the secondary side is wound in the Y ground configuration. And now for the grounding, we can have different grounding: solidly grounded, resistance grounded, reactance grounded, different grounding configuration. Then another example is white ground. Then another example is delta. So the high voltage side is wound in the delta configuration, and the low voltage side wound in the delta configuration. So this is an example of a good answer that you can give them if you are asked that question. Any other interview that you will basically be part of as a discipline engineer, that is a power system design engineer, as a maintenance engineer, as an operator, as a maintenance technician. Yeah, this is how to answer this question very good and score all the points. Another typical example that you can be asked as a discipline engineer, as a maintenance engineer, as a maintenance technician, as a relay technician, as an operator, as a construction engineer, explain to me the power transformer. This is how you answer it. Okay, so a good way to answer this question is basically draw a sketch. And believe me, interviewers basically like sketch. It's because this the saying that pictures are more than 1,000 words, right? Okay, so what you need to do is basically sketch this on the board and basically explain it this way. Okay, so for a power transformer, this is a section of a power transformer single phase arrangement where I have my primary winding. wound on this section of the core, and my secondary winding wound on this section of the core. And this one is a cross section of the core or magnetization branch of the power transformer. So the primary side can be an example of the high voltage winding, and the secondary side winding can be an example of the low voltage winding, right? Okay, so voltage is impressed on the high voltage side, right? Okay, so you have voltage being applied here, as you can see over here, right? So once you apply that voltage to your primary winding or your high voltage winding, as it is shown over here, right, primary current flows. So the primary current that is flowing is IP, right? Okay, so that primary current is going to flow through the core, right? And basically it's going to create an electromotive force and create an electric field that will basically align the magnetic domains of the core, right? Okay, so as it aligns, it creates a magnetic flux. So this is the path of the magnetic flux, as you can see over here, right? So as the magnetic flux flows through the core, it basically flows through the secondary winding, right, which is the low voltage winding. And as it links the low voltage winding, it induces a voltage in the low voltage winding. So it's more of an electromagnetic induction. The transformer action is more of an induction, right? So once the voltage is induced in the low voltage winding and you connect a load here, you have a secondary current that is flowing through the secondary winding of the power transformer. So this is an example of how to answer this question if that is posed to you in your view, and basically score all the points. Next question. Tell me the types of transformers that we have out there. Okay, so this is how you answer that question. We have power transformers, right? Okay, so we can have a power transformer at the transmission level, and under the umbrella of power transformers, we can have a step-up transformer. We can have a step-down transformer. And a typical example of a step-up transformer, which is basically used in a generation, substation, or switchyard, is, let's say, it steps the voltage from 13.8 kV to 115 kV to 230 kV, 345 kV, 500 kV, 765 kV, and so on, right? Okay, another example of a step-down transformer is once at the transmission level substation, right? You can have a transformer, let's say 115 kV, that can step down to 69 kV, to 34.5 kV, or 230 kV to 69 kV, or 34.5 kV, right? Okay, so this is an example of a power transformer that is used as a step-up transformer or a step-down transformer. Then let's talk about distribution transformers. Power transformer, you know, we have distribution transformers that are used at the distribution level, that is at the tail end of the power system network, right? Okay, so for distribution transformers, you can have a step-up transformer or a step-down transformer, right? Okay, so for a step-up transformer, when it is used in the distribution, that is when basically more of an upgrade, you know, modification of the network, where basically the voltages are being stepped up to be used, let's say, for an industry that is being constructed in that distribution network, where basically, let's say the distribution voltage level is 30.8 kV, and you're stepping it up to, let's say, 69 kV or 34.5 kV. Then, most often than not, at the distribution level, a lot of the transformers are step down, where you have a 13.8 kV to, let's say, 480 volts, right? 34.5 kV to 4.16 kV or 6.9 kV or 34.5 kV to 480 volts, right? So those are the type of step-down transformers, and about 90% to 95% of the transformers are on the distribution level are step-down transformers. Then we also have special transformers, right? Okay, so for special transformers, typical example is arc furnace. Yeah, because they call them special transformers is because they utilize a very high current, right, for their application in the arc furnace. Then we also have traction transformers that are used in high-speed rail trains, right? Next question that you can be asked during an interview on the power transformers is, tell me about the different transformer construction and configuration that you know. And this is how you answer the question beautifully. The first one is the free breather or the open conservator tank, right? Okay, so sometimes basically you want to prove yourself to the interviewing panel that okay, you know what you're talking about, right? Okay, so what you can do is okay, you can tell them that okay, let me sketch for you a typical example of how an open a free breather or open conservator tank look like. So this is the main tank, right? Then you have the conservator tank, right, on top, right? And from the conservator tank you have a downcomer piping that comes to the top of the main tank, right? Okay, so inside the conservator tank you have oil, right? Then on top of it you have a bladder, right? Okay, then coming down is your air breather or the silica gel, right? Okay, so the silica gel basically it's the one that filters and dries the air, right, when the transformer basically breathes in and out. The goal is basically to prevent moisture from intruding into the oil that is acting as a reservoir for the main tank. So this is an example of how an open conservator tank looks like. Okay, so another example is a seal type. Okay, so for the seal type, right, you have oil, right, and on top of the oil, to protect the oil from the external element, right, the goal is basically to mitigate external weather elements like moisture, oxygen, nitrogen from intruding into the oil, to oxidate. And when the oil oxidates, basically it defeats its purpose, right? It functions. So what they do is they put a cushion of nitrogen blanket, right, to basically act as create that positive pressure on top of the oil to prevent that external contaminants from coming into oxygen, moisture from coming into contact with the oil. So this is how you explain yourself, right? And basically with sketches, and basically that will score you all the points that you deserve during a typical interview. Next is a dry type transformer, right? Okay, so for dry type, that are used mostly in the very low voltage and sometimes a little on the medium voltage, right? Okay, up to I think up to about 13.8 kV level, and I mean they are progressing to about 34.5 kV for dry type transformers, right? Okay, so dry type transformers are basically the winding is encapsulated in an epoxy, right? Basically, and what the epoxy does is it provides the insulation strength, and at the same time it is basically also removing the heat from the winding and also protecting the winding from the elements, right? So that's an example, a typical example of the different types of transformers that we have, configurations that we have out there. Next, typical very good question, and that you can be asked. And this one is a very popular one, and basically you can be asked during an interview. So let's see. Tell me about the different components of the power transformer. Okay, so this is how you answer. Okay, so that's how you answer this question. The components of a power transformer. The first one is active component. Okay, so the active component, it's basically your core and core, right? So this is phase A, and phase A basically has your high voltage winding and your low voltage winding. So, and your limb, right? Okay, so if this is the limb or your core, right? Over the core is an insulation material, right, to provide a ground plane to the low voltage winding. So, right on top of the insulation on the core is your low voltage winding. Then over the low voltage winding is a high voltage winding, right? But in between that are layers of cylindrical layers of, just like you are seeing over here, cylindrical layers of various sections of insulated. It's more of an insulation coordination, right? Okay, so that one is all based on design, where basically the cylindrical insulation is arranged, to basically provide that dielectric strength for that phase of the link. Then it also includes basically your clamping, right? Okay, so basically, as you can see over here, the clamps, the core and clamps, right? Okay, all these are basically form the active component, and the clamping is done so that the transformer can withstand short circuit conditions when it basically encounters any short circuit whilst it is in operation, and also to withstand the normal vibrations that occur when the transformer is in normal operation condition. Next is a low tap changer. Okay, so as you can see over here, right, we have the low voltage winding that is wound. Remember, the low voltage winding is inside, right? The first winding after the core, right? Okay, so part of the low voltage winding are taps, right, that are brought out. The goal of the tap is to provide that regulating voltage to the load. So we can have an example is 16 taps above, 16 taps below, so 33 taps, right? Right? Okay, so you change that taps based on the output voltage that you want for the load. Okay, so it's all based on design, right? Okay, so basically you're able to achieve that 33 taps, and based on various voltage range, and like let's say plus or minus 10% voltage regulation range. Then we can also have a de-energized tap changer, right? So the de-energized tap changer is located on the high voltage side, right? So if, let's say, the high voltage winding, we have 5 taps. If this is the nominal position, it means that we have 2 taps above, 2 taps below that, okay? So that allows you to change the incoming voltage to the high voltage side to be able to achieve the corresponding voltage on the low voltage side that is required for the load. Okay, and that is done utilizing the de-energized tap changer, and the transformer has to be de-energized before you can change those taps. Next is the low tap changer. Like I mentioned, the low tap changer, the transformer taps can be changed whilst the transformer is in operation. Next is the bushing, and this is an example of the bushing, as you can see over here, right? Okay, so we have the leads from the high voltage winding, right? Remember, I made mention that this is the construction of each phase. This is phase A, phase B, phase C. In each phase, if this is the core, they call it the limb, right? Over the surface of the limb are insulating layers, right? The goal is to provide that insulating layer, provide a ground plane, and to protect the low voltage winding from going to ground. So on top of the insulating layer, it's the low voltage winding, right? Okay. Then in between the low voltage winding is the high voltage winding, but in between that we have cylinders of insulation that has been arranged, right? The goal is basically to provide a path for the oil to flow in between the low voltage and the high voltage, right? It's arranged in cylinders, right? So the oil flows in here freely to remove the heat, and also to provide a dielectrical capability in between the high voltage and the low voltage. So the leads from the high voltage winding are what you see over here, and that is what goes to the bushing connection over here. So this is the connection for the bushing for the leads. Then the leads go through the bushing, then it comes out for outside connection. Next is the winding temperature gauge, right? Okay, so the winding temperature gauge, what it does is basically to provide an indication of the winding, and matter of fact, the hotspot, right? Hotspot temperature. So for the hotspot temperature, we have a dedicated CT, right? That measures the low voltage load current, right? You have a low voltage and basically that goes to the load, right? So a dedicated CT is mounted most often than not is, let's say, in phase B, right? That measures the load current, and that load current is connected to a heater, right? To build up the corresponding heat in terms of temperature, right? Then after that, a gradient is added to it to achieve the hotspot. So that is how the winding temperature gauge basically provides an indication of the hotspot temperature inside the transformer. Next is the oil temperature gauge, right? Okay, so the oil temperature gauge, basically, we have a transformer that is filled with oil, right? All the way to the bottom, right? You need to know the top oil temperature, right? And that's what the oil temperature gauge does. Next is the Buchholz device, right? Okay, for the Buchholz device, and it is mostly installed in free breathing open concentrated tank transformers. Okay, so you have a main tank right here, right, filled with oil. Then on top of it is the concentrated tank, right, reservoir that has oil here, right? Okay, so in between the concentrated tank and the main tank, we have a downcomer piping, right? And at the middle part of the downcomer piping is your Buchholz device. Okay, so the Buchholz device has three functions, and we'll come to that in another question, and I'll explain to you, right? Okay, so the Buchholz device is installed in between the conservator tank and the main tank, right? And its goal is basically to provide a low oil level indication. You know, if let's say the transformer is leaking so much oil that the concentrator tank has replenished the depleted oil, and the concentrator tank is empty, and a vacuum has been created here. Another function is, let's say, if there's a true fault that creates a pressure wave, this oil will flow backwards, and it hits basically a switch that activates the Buchholz device. Another example is incipient arcing. Due to, let's say, if you have a broken strands, you can have a broken strand from here, right? This low voltage tap leads, right? We can have broken strands from this bushing connections, right? Right. So when you have such a situation, you have a broken connections like that, what is it going to do? It's going to create an arcing, right? That arcing will create basically acetylene gas, right? And basically this acetylene gas, will start building up. They call it incipient. It start building up, then it start rising to the top, right? It will start rising to the top and collect into a chamber inside the Buchholz device. And based on the volume of gassing, it basically creates a wave, right? It's rising up because gas is lighter, right? Okay, but after a certain volume is trapped inside this Buchholz device, it acts as a wave, and basically it activates a mercury switch, or to provide an alarm indication for you to investigate. Next is a sudden pressure device, right? Okay, so sudden pressure device basically is the first line of defense for through fault, or basically closing fault, right? Okay, so if you have a transformer and you have a closing fault is having a fault in close proximity to the power transformer, but that basically creates a movement inside the transformer. Basically, you have all this inside here filled with oil, right? So if you have a fault that impinges, right, it's going to basically create a pressure wave, right? And that pressure wave is going to basically hit the bellows of this sudden pressure device and activate a switch basically to provide the alarm indication or the tripping indication that you want. Next is the pressure relief device, right? Okay, so the pressure relief device is usually mounted on top of the transformer. And it's the last line of defense for the power transformer, right? Okay, so because this comes into play when you have all the protection schemes fail, right? You have your primary protection, that is differential protection failing. You have the backup protection failing, overcurrent failing, right? Then you have other devices, other protection schemes all failing, right? So by the time the pressure, the electric, the fault current would have evolved, would have grown, and basically evolved into a huge electrodynamic force, right? And a huge pressure inside the transformer, right? There has to be a way of basically, bringing this out, pressure out. Other than basically the main tank is going to explode, right? Okay, so this pressure relief device has been designed and set to detect that amount of pressure buildup and basically open up to expunge all the oil that is inside the transformer. More of a safety factor, for both personnel and also for buildings in close proximity to the transformer. Next is the control cabinet, right? Okay, so for the control cabinet, it is usually mounted on the side of the transformer, and it has all the wiring basically for controlling all these control devices, right? You see over here, CTs that are basically you see the CTs over here, right? CTs for mirroring, CTs for protection. The wirings are brought into the control cabinets, right? Okay, and basically for all the auxiliary devices, all the wiring are brought there. You have relays, right? And it's the interface between the transformer and your SCADA system or your DCS system, through your RT, remote terminal unit, right? Okay. Next is the radiator, right? Okay, so the radiator is mounted on the sides of the transformer, and it's basically your heat exchanger, right? Okay, so on the side of the radiator, you can have cooling fans if you have forced air condition, for the transformer. On the other hand, if you don't have that, then you have a natural air flowing over the thin sheets of the radiator. Next is consolidated tank, right? Okay, so I explained to you what the consolidated tank does, right? It's for free breathing consolidated tank, open consolidated tank transformers, and its purpose is to act as a reservoir to replenish the level of oil in the main tank. If let's say you have a leak, or let's say throughout its operation of the transformer, definitely basically contracting, expansion, the level definitely gets down, and it's the function of the consolidated tank to replenish this level as the level basically decreases. Next is cooling fans, right? Okay, so the cooling fans are mounted on the sides of the radiator, and you can have different stages of cooling fans based on the size of the transformer. I've seen cooling fans all the way as big as all the way to stage 4. So that's to tell you how big that transformer is, right? Okay, then the purpose is basically to blow over the surface of the radiator to remove the heat. Next is the surge arrestor, right? Okay, so the surge arresters are basically located in close proximity to the bushings, right? Okay, its purpose is to protect the transformer from overvoltage conditions due to lightning strike or due to switching surges, impulse that can damage the transformer insulation, both the paper and the mineral oil. Okay, so now let's walk through basically all the components that I made mention in the previous slide, right? Okay, so in the previous slide, I showed you, the internal components, mainly the active component, that is the core and coil, how they look like, So they say the pictures are worth more than 1,000 words. For the other components, basically externally, I'll show you, how they look like. Okay, so this is the bushing, how it looks like. Okay, so external, this is the high voltage bushing, and this is how you can locate or differentiate between the high voltage bushing and the low voltage. It's based on the size. So as you can see, this one is far bigger than this one. So this is the low voltage bushing, and this is the high voltage bushing, right? Okay, and the reason why these bushings are slanted from each other, right? This is phase A, phase B, phase C, right? The reason why the phase A bushing is slanted a little bit at an angle to phase B bushing is because of the difference in dielectric strength between oil and air. As you can see over here, right below here is oil, right? The transformer is filled with oil, right? And here is air, right? Because the dielectric capability or the strength of oil is higher than air, it means that two conductors can be put closer together at the design requirements, right, to prevent arcing between them, right? And over here, because air has a lower dielectric strength, it means that the spacing has to be wider. So that is why you see those bushings at an angle. So this one is the conservative tank I made mention. This is how the conservative tank looks like, right? So, like I told you, inside here you have oil, right? On top of the oil is a bladder, right? That is connected to the outside world, to the air breather, right? That has silica gel, right? Right? And the silica gel, you have oil, right? And you have holes, right? That allows basically air to flow over there, right? So the breathing in of air goes through those holes, right? And the oil layer regulates the amount of air that is intake, right? So this is your silica gel beads, right? Okay, so as the air goes through the beads, it removes the moisture, right? It removes the moisture. When the transformer is breathing in air, when it contracts during the cold season, right? Okay, so the air that is coming here is dry before it comes into contact, with the oil. The goal is basically to protect the oil from oxidative elements of the weather. Okay, so this is the low voltage winding bushing, right? And inside here are your bushing turrets, T-U-R-R-E-T. And inside here you have the cities, right? Okay, so the cities you can have about 2 or 3. Usually they put in spares, right? Okay, so you can have one for mirroring and one for protection, right? And these are basically all wired and it goes to the control cabinets, right? Okay, so this one is for phase A, phase B, phase C. Okay, so the high voltage side, similarly, this is the turrets, right? And inside the turret is filled with oil and has cities, about 3 of them. Let's say utilizing one for mirroring, one for protection, and the other one as a spare. Okay. On this side is the surge arrestor, right? And I explained to you what a surge arrestor does, right? It to basically protect the transformer from overvoltage condition, from lightning impulse strikes and switching impulse strikes. Right? Okay. And inside the surge arrestor, it's a metal oxide varistors, a non-linear, semiconductor, right? During normal operation of the surge arrestor, basically it offers a high impedance from ground plane, right? And only leakage current flows. But when you have a surge, lightning impulse surge, basically due to the high voltage, it basically changes from high impedance connection to a low impedance connections. It clips the voltage, then discharges the current to ground. Over here are your winding your temperature indicating devices, right? We have indicating devices for the high voltage side and for the low voltage side, right? Okay, so for the high voltage side, you can have a winding temperature indicator, right? Basically providing hotspot indication for the high voltage winding and the low voltage winding. And similarly, oil temperature, top oil temperature indication over here, right? Okay. For the hotspot temperature indication, it uses a dedicated CT, right? That is located in the low voltage winding. Let's say phase B, right? That is connected to the load. So it is measuring, the CT is measuring the load current, right? So that load current is connected to a heater, right? Right? So the heater basically builds up heat, and the temperature is measured from the heater, right? And a gradient is added to achieve the hotspot. So that's how the hotspot temperature is achieved. Next picture. They said pictures are worth than 1,000 words. Okay, so this is an example of a transformer, and to show you the components, right? Okay, so this radiator, it's more of a cooler arrangement. Okay, this is a little bit different from the traditional or conventional radiators. Okay, so it has an inbuilt more cooling capability than the conventional surface radiators, right? Okay, so the fans are basically, the radiator is inside, right? That allows basically the removal of the heat from the oil, right? Okay, so I made mention that some of the transformers utilizes pumps, right, to pump the oil, right, through the ducts, right? The cylindrical arrangement of the insulation, right, in between the high voltage and the low voltage winding, right? We have cylinders that have been in to basically to pump the oil through that. To force the oil through that, you need pump, and this is how the pumps are located, right? And its goal is basically to force the oil through the ducts and to remove the heat as quickly as possible to achieve the required temperature rise per design. And this is an example of the concentrator tank that I explained to you in the previous slide, right? On the side of the concentrator tank are oil level gauges, right? And I explained to you what the concentrator tank does, right? It's acting as a reservoir, okay? And its goal is to replenish the depleted oil level, either through a leakage or due to its continuous operations. As basically the oil expands, contract for a long period. Basically, that definitely the oil level is going to go down, right? Okay, so its goal is to replenish that depleted oil in the main tank. Okay, so this is the bushing on the high voltage side, and this is the bushing on the low voltage side, right? Okay, so as you can see over here, right, this is basically the oil coming from the radiator, right, after it has been cooled, and it goes to the bottom of the transformer main tank to repeat the cycle, right? Okay, then basically the oil gets heated, through a convection action, right? It expands, right, and rises up, then it goes through the radiator, then the cycle repeats. Okay, so like I indicated, pictures are worth more than 1,000 words, right? Okay, so as you can see, you're now seeing more pictures of to basically describe the different components of a transformer, and that helps you to be able to answer the question, much deeply, to score all the points that are okay. So, I explained to you, this is a concentrator tank, right? And I explained to you what a concentrator tank, right? This is the high voltage bushing. This is the low voltage bushing. These are the connections, interface to the external side, right? These are the conductors that is connected to the low voltage bushing, and these conductors are connected to two conductors in parallel, right? To basically share the phase currents. On this side is the control panel, right? As you can see over here, right? I told you that, I indicated that all the wiring that comes from all the auxiliary devices all coming to the control panel. From the wiring from the CTs, the wiring from the pressure relief devices, the wiring from the sudden pressure relay, right? Everything comes in here, and basically this is the interface with your RTU to your SCADA system or your DCS. Next is another picture of a smaller transformer. So this is an example of a sealed unit. Remember, there are many types of configurations of power transformers in the previous slides based on the question over there, right? I explained that we have the sealed type, right? As you can see over here, the top of the transformer is sealed, and inside that you have oil, right? On top of the oil is a seal of a cushion of nitrogen that has been put over here to pressurize to create a positive cushion pressure. As you can see over here, this is the enclosure for the nitrogen bottle, right? So you have a connections inside here that goes there to basically to provide that nitrogen pressure, as you can see over here, right? Okay. For the temperature gauges, this is an example of the temperature gauges, as you can see over here, right? The oil temperature gauge and the winding temperature gauge. And usually the winding temperature gauge, we have one for the low voltage side and for the high voltage side. Then over here are other auxiliary devices, right? Okay, so as you can see over here, this is basically an example. Pretty much sure this one is the top oil thermocouple, right? That goes in on top, and it comes in here before it goes to the gate. It comes in here to the control cabinet before it goes to the gate. So this is a typical example of how the wiring configuration of the auxiliary devices look like. Next is our stage cooling fans, right? Stage cooling fans. Remember, I did mention that there are different types of radiators, right? In the previous couple of slides, I showed you of a different type of radiator that is more of a cooler. They call it a cooler because of the high capacity and high capability of its removing cooling, right? This one is quite different. This one basically you have the radiator. This is the radiator. As you can see, they are very thin sheets, right? That allows air to flow it naturally, right? At the same time, it has the stage cooling fans, right? So this is how the cooling fans look like, right? That are powered by auxiliary voltage 480 volts, right? That comes from an MCC switchgear, right? That provides power for these fans. Okay, so it go basically the fans usually most often than not are not on, right? Unless of course the transformer picks up for load. So let's say if you have a 30 MVA on and 40 MVA on, right? On means oil is flowing naturally, right? And the air is flowing naturally. The fans are not on, right? But once the transformer exceeds this threshold of load, right, above 30 MVA towards 40 MVA, then that is when automatically, based on the sensing of the top oil temperature, right, and the winding temperature, right, it basically turns this stage cooling fans on to be able to remove, because the transformer has picked up additional load, right, and it should be able to remove the heat from the oil as quickly as possible to be able to achieve that design temperature rise for the oil temperature rise and the winding temperature rise about 65 degrees C above design ambient temperature of 30 degrees. Okay, so this is an example of basically connection to the low voltage side, right? The low voltage connections are coming in here. Next is another beautiful, very good question that you can be asked. What does DYN1 and DYN2 vector configuration of the power transformer? What does it mean? Okay, and this is how you answer. DYN1 means that the high voltage side of the transformer is connected in a delta configuration, right? Okay, so if you have a transformer core, right, in 3 phases, right? Okay, this is how it looks like. So below this you have the bottom yoke, bottom yoke. On top of it is the top yoke. Right? This is phase A limb, phase B limb, phase C limb, right? So this is how the flux traverses. So the flux flows like this. Okay. On the surface of the core, right? Remember the core is a ground plane, right? So to protect the low voltage winding, you have an insulation layer that is wound, that is put on the surface of the core, right? An insulation layer made of paper, and basically that is wrapped around the core. Then they put the low voltage winding, basically they slide it on top of it, right? Okay. So this low voltage winding is wound in Y grounded, right? Y grounded. And the grounding could be solidly grounded or resistance grounded, low resistance grounded, or reactance grounded, whichever configuration, grounded scheme that you are utilizing. Then, in between the low voltage and the high voltage, you have a basically cylindrical corrugated high density wood insulation. Remember, I told you that they are put like this. If you're looking on top from a pictorial view, this is how the insulation look like, right? You have the low voltage, you have the core, and you have the low voltage, then you have this cylinders. Then you have the high voltage winding, like this, right? You have the low voltage winding, then you have these cylinders. In between, it's what they call the air gap, where basically their oil is flowing, right? Oil is flowing to remove the heat, right? Okay, so basically all the cylinders act as a insulating barrier between the high voltage and the low voltage, right? Okay, so the high voltage winding is wound in the delta configuration. So, and the one you see over here, right? It's just like the clock system, right? We have 12 o'clock here, 1, 2, 3, right? In between the 12 o'clock and 1 o'clock is 30-degree angle, right? So that is why the high voltage side is leading the low voltage side by 30 degrees, because the one is is an equivalent of the clocking system, where between 12 o'clock and 1 is a 30-degree angle. Next is a DYN 2, 11. DYN 11, right? Okay, so if you look over here, 11 o'clock is right here, right? Right? If you look at this, this is like 330 degrees. Okay, so in that case, it's the other way around, right? Similarly, the high voltage side is wound in the delta. The low voltage side is wound in a Y configuration, Y grounded configuration. But this time, the low voltage side leads the high voltage side by 30 degrees. Basic terms. Another beautiful question that you can be asked is, tell me about the different standards, industry standards that can be utilized on power transformers. Remember that even you have a best practice that you utilize. Those best practices are built on these industry standards. That's IEEE and IEC. So this is how you answer that question. The first one that that I can think of is IEEE C571290, right? Okay, and basically this provides all the test code, all the different testing that can be performed on a liquid immersed distribution transformer, power transformer, and regulating transformer. Then IEEE C57.91 this provides the guide for loading of the power transformer. And you can go further by saying that, okay, sometimes industrial plants, utility plants, don't have a choice than to overload a transformer, right? But that overloading can be done based on following the standards. What the standard is saying that you can overload, but the overloading, the percentage overload has to be done within certain required duration. Let's say you are overloading the transformer, let's say 150%. Okay, go ahead and overload it, but I want you to overload it within, let's say, 4 hours, not more than 4 hours, right? The goal is to protect the hotspot temperature, right? To limit the hotspot temperature, because as you know that if the hotspot temperature, let's say design hotspot temperature is 110 degrees, right? Okay, so let me show you how they design wise they achieve the hotspot temperature. Let's say if you have a design ambient average temperature, right? Average temperature of 30 degrees that is used for design, right? Plus 65 degrees is usually the ambient rise data is used in the design, right? So 30 plus 65, what is it? 95, right? 95 degrees, right? Okay. So to achieve a design hotspot temperature, they put in a margin, right? So as you can see, the margin is what? 15 degrees Celsius. That is built, right? That allows you, basically to overload the transformer to be able to stay within this. So, but don't go beyond 110 degrees Celsius. So as you are overloading the transformer 150% within the allowable per the standard, right? You still need to, monitor your hotspots, right? To prevent heating of the paper insulation and also heating of the oil to create to basically what it's going to do is going to degrade your insulation, and your insulation strength is going to decrease, and basically your degree of polymerization, the strength of the paper insulation is going to go down. Next is IEEE C5793, right? Okay, so this provides a guide on how to install a liquid immersed power transformer in the field. So this basically comes into construction, where a transformer is installed. Next is general requirements, right? General requirements C571200, right? Okay, so the general requirements are basically an example is this standard. You can say that this standard provides how impedance can be selected on a distribution transformer, or power transformer, or regulating transformer based on the MVA or KVA outputs, right? This standard also delineates interpretation of the nameplate of a power transformer or regulating transformer or distribution transformer. So basically, what you're telling them that, okay, this is the standard, but at least you need to tell them about 2 or 3 items that you have utilized out of the standard. That basically let them know that at least you have used the standard before, or you know what you're talking about, right? Okay. Next standard is C57104, right? Okay, so this is a guide that they use for interpretation of gases, right? Okay, before if let's say the gas exceeds the total combustible gas criteria, then basically you can move to the diagnosis stage. Okay, so what you can tell them is, okay, this standard is basically use to tabulate the gas concentration after you perform a DG, right? Okay, so it's been grouped into 4 conditions: condition 1, condition 2, condition 3, condition 4, right? Okay, so the different gases, right, starting from carbon dioxide, CO, carbon monoxide, methane, right, ethane, ethylene, acetylene, right, and hydrogen. Okay, all these gases and its range criteria has been grouped into condition 1, condition 2, condition 3, condition 4, right? Okay, so as your gas's concentration, then total dissolved combustible gas, right, out of this. So out of all these gases, there are combustible gas. A typically combustible gas is hydrogen, acetylene, right? Ethylene, right? Okay, so based on all these, right? Okay, and the ranges that you get, and let's say if you get into condition 3, condition 4, then that is when you need to take some action, right? Through basically condition 3 is when you need to plan to basically validate, right? Validate, it means that you collect another oil sample, take it to a different lab to validate your results. Then after that, you need to implement the corrective actions. That is filtration, de-energize the transfer, filter and degas, right? Then based on, let's say if you have a sludging acidification, then you need to rejuvenate, right? Rejuvenate the oil and bring the oil back to its normal condition, right? Okay, so once we tell them that, then basically they know that you have used this cement and you know what you're talking about. Okay, so based on, let's say if you have a total dissolved combustible gas, right? Then in condition 3, condition 4, then you move to the diagnosis stage. So diagnosis stage is where you utilize the Duval triangle, the Rogers ratio, right, to diagnose the type of fault you have, right? Whether it's a PD activity, right? High temperature, T1, T2, T3. T1 below 300 degrees, T2 300 degrees to 700, and T3 above 700 degrees, right? Okay. Then basically, an example of a above 700 is acetylene gas. That's basically it's a high temperature gas. Okay. Next standard is field testing of electrical apparatus, and basically this is for all electrical apparatus. But the power transformer is an electrical apparatus. Basically, it relates all the electrical testing that has to be performed. And basically, you can cite examples, right? Okay, these are the type of testing that can be performed on the power transformer. Turns ratio, insulation resistance, and polarization, determination of polarization index, impedance, capacitance, tan delta, power factor, right? Winding resistance, right? So if you tell them that all these list them, then at least they know what they know that you know what you're talking about. You have to utilize the standard. You don't have to tell them this is the standard, this is the standard. No. Anybody can say that, right? What you have to do is at least tell them about 3 or 4 things out of the standard you have utilized. So that itself let them know that you know what you're talking about. Okay. Next is standard is C57106, right? Guide for acceptance of insulating liquids, right? Okay. So basically, this boils down to oil quality testing, right? And DGA, right? Okay. So DGA, or the gassing that you see over here, right? This guide is basically tells that, and also oil quality. That is moisture level. Breakdown voltage, right? Acidity, neutralization number, right? Furan compounds. So these are all the typical examples that you can give them, just to let them know that you know what you're talking about. Okay. Another good question is tell me about the different factory acceptance testing that can be performed on power transformers. Okay, and this is how to answer it. First one is a routine test, right? And next one is design test or type test, and special test. Okay, so you don't just have to tell them that okay, these are the tests that are about, but you have to break it down. Okay, under routine test, what are the type of testing that can be done? You have to list about 4 or 5, at least minimum about 4 tests that can be done for routine test. For design test, minimum about 4 tests that can be done. Special test, minimum about 2 or 3 tests, right? That can be done. So that itself tells the panel of interviews that this guy knows what he's talking about, right? Okay, so for an example of typical examples that we can give them, it's oil breakdown voltage, dielectric breakdown voltage testing, and that is done by oil sample collection, where it is sent to the lab, usually 2 different labs, where the testing is done, right? Okay, measurement of moisture, right? Okay, and basically to determine the moisture content in insulation, in the paper and the oil, right? Okay, so you can go to further to the extent of, let's say, an example of the criteria, that is industry criteria for based on different voltage levels of the power transformer, right? Acceptance criteria. So that itself gives you, more plus, more extra points, right? Okay. Then test ratio, voltage ratio or polarity, vector group test. Then winding resistance. Then copper loss and impedance testing, right? And load loss, right? Then vector configuration, extension, current, no load loss, insulation resistance and PI, right? And induced voltage tests, right? Okay. Then where PD activity is performed. Then power factor testing, right? Where basically capacitance and tan delta is performed, right? Okay, high pot test, separate high pot test for high voltage side and low voltage side. Then functional testing of the auxiliary devices that you see, right? And these are sudden pressure device, pressure relief device, right? Glucose device, right? These are all the the auxiliary function, and basically your temperature gauges, right? Oil temperature gauges, winding temperature gauges, right? And the fans, right? Next is the ratio and polarity of the CT. The CTs that you see inside the turret of the bushings, right? Okay, they also have to be tested, right? Okay, then there's testing for it, the turns ratio and the polarity. Then for your control circuit, you also need to perform insulation resistance, and testing is done at 250 volts, and not more than 500 volts. Okay. Next, it's design test, right? Okay, so design test, basically you tell them, okay, design test comes into play. Let's say if it's a new design of a transformer comes, then let's say they have to test it, and that testing results becomes the fingerprint, that the manufacturers or the OEMs keep, and so that sometimes the routine and the design test, some of the design test testing results are part of the routine. So in the future, if let's say a customer wants to buy a transformer, right, and he will ask, if he wants to cut down costs, right, okay, what he's going to say, okay, if you have done the design test, show me the results of the design test. So out of the design tests that are basically shown on the routine test, then basically the customer can say, okay, you don't need to perform this test. For instance, the turns ratio are part of the routine test. So it means that once you're able to show me the design test, the type test results for this transformer, you don't need to repeat that testing, right? Okay. Winding resistance test, same thing, right? You don't need, But what differentiates it's a temperature rise test, right? Temperature rise is a typical design test that is done, and impedance voltage test and vacuum test basically is to test for leaks, right? Then capacitance and tan delta and lightning impulse test. So these are tests that are type is for a certain type of design, making sure that that design of transformer is going to function, per design, and it's going to operate reliably when it is installed in the field throughout its whole operating life cycle. Next is a special test, right? Okay, so sometimes the customer comes up with certain needs of a test that needs to be done, right? Okay, and they have to provide a list of special tests as part of the specification that is given to the manufacturer. Okay, so this is an example of a typical type special test that you can say, okay, zero sequence impedance testing. Okay, so this testing is basically done to determine the zero sequence impedance for the protection relay engineer to be able to calculate its single line to ground fault, double line to ground fault, to be able to set its relays, right? So that is why they do the zero sequence impedance testing as a special test. Next is the harmonic content of the no load current. Okay, so as part of the differential protection, right? Okay, there's something they call magnetic inrush, right? Okay, and magnetic inrush can be a nuisance and can cause the transformer to trip, during energization if you don't have the proper setting in place. Most often than not, these transformers come from the factory with a factory default, and it is up to the protection relay engineer to update the settings based on actual component, actual data. So what some of the customers do is they tell the manufacturer, okay, you need to perform, basically provide me the harmonic content of the no load current, right? The second harmonic content percentage-wise, fourth harmonic content percentage-wise, third harmonic content percentage-wise, fifth harmonic content percentage-wise, so that I can use it to set my magnetic inrush inhibits to prevent nuisance tripping. Let's say if after the testing is, let's say this one is 20%, right? This is how much inrush. So based on that, the relay engineer will do his set. Next is functional testing of auxiliary devices, pressure relief devices, glucose, sudden pressure relief devices. Okay, this is considered as a special test that has to be done, for the customer. Next is acoustic sound level, right? Okay, so sometimes, certain power transformers has to be located in certain vicinity, certain areas, certain neighborhoods, right? Certain facilities, right? Areas. And based on the city ordinance, right? Based on the city ordinance, sometimes the city ordinance will require certain noise in dB emissions, right? To be curtailed, right? Okay, curtailing the noise, right? Okay, so the vendor, or no, the customer will go to the city and ask for its noise emission acceptance level, and that is what the customer is going to provide to the manufacturer, right, or the vendor, that you need to meet this noise level emission, and the testing is done to achieve that. Next is the power that is taken by the fans and the pumps, right? Okay, so if you have a power transformer, right, that has fans that are installed on the radiator, and also pumps that are located below to basically pump the oil throughout all the various sections of the ducts, right? Okay, so what is going to do, it's basically after the testing, right, the manufacturer is going to provide that testing results, the amount of power that is going to be taken by these auxiliary devices, right, so that based on that, their customer can determine the amount of size of the MCC bucket that it needs to provide, power that it needs to provide from the MCC switchgear to be provided for these auxiliary devices. Next is other special dielectric testing, okay, and basically we have DFR, dielectric frequency response, basically where you vary the frequency to achieve different power factors, right? Okay. Then also switching circuits, impulse switching circuits. Let's say if the transformer is going to be located in the vicinity where there are switching action that needs to be taken, right? Okay, so that switching action can create switching impulses, and the testing has to be done to make sure that the insulation system can withstand that. Next question is, tell me about a site acceptance testing for power transformers, and this basically comes into play when the transformer is shipped to the site and installed. Okay, so for site acceptance test, right? Okay, so the transformer, depending on the size, is shipped to the site with all these gauges basically in place. The oil temperature gauge will be in place, right? All these and the piping for the air breather might be removed. Okay, the fans are removed, right? and the oil pump will be in place, and all these will be in place, right? The concentrate tank will be removed, and the bushing will be removed. The transformer will be drained. All the oil will be drained and will be put in barrels, right? Okay, and the transformer will be filled with dry air, right? Okay. So once it gets there, all these components have to be inspected, right? Okay. And the bushings and all those things have to be inspected to make sure that they are in perfect conditions and not damaged. And also, there's something they call dew point, right? The dew point of the air that is inside the transformer, because the transformer is drained. The bigger size transformer, the oil is drained and filled with air. So you want to make sure that there's no intrusion of moisture, right, inside the transformer. So that is why you measure the dew point, right? Okay. So then after installation, right, okay, you test all these functionally, test all these devices, okay, and so that's what they call operational testing, right? Then you perform basically, integration of the alarm and the trip circuits, right? Okay, perform testing of the whole sequence, right from the auxiliary devices to your DCS system or your SCADA system, right? Or that part, or your tripping system, your tripping breakers, everything. That testing part is basically, if it goes through auxiliary relays, all that part is tested. Then insulation resistance and polarization index. Then operational check of OLTC. Actually, insulation resistance testing, not polarization index, but insulation resistance testing of all the circuit. Next is oil breakdown voltage testing, right? Measurement of moisture, right? Okay, so this is done after installation when you have filled the transformer with oil and you have energized the transformer, right? Okay, let it soak for about 24 hours. So that is when you collect that oil sample to be sent to the two different labs to test the oil to make sure that it doesn't have any moisture, during transportation and during filling. Then also, turns ratio, and voltage ratio, polarity, then winding resistance testing, then impedance testing, then polarity and excitation current, insulation resistance, and polarization index. This one is for the power transformers, but for your auxiliary circuits, it's only insulation resistance. And remember, I told you that the insulation resistance is done at 250 volts or 500 volts, very low voltage, right? Okay. But for the power transformer, the insulation resistance testing is done at 20,000 volts, 2,500 volts, and 10,000 volts. And next is the power factor testing, right? Then functional testing of all auxiliary devices that I explained in the previous slide. Then ratio testing, polarity testing of the CT, then insulation resistance of control circuit. Next, very good question is to tell me, as a discipline engineer, and as a discipline engineer, you can be a field engineer, maintenance engineer, a construction engineer. If you have a power transformer that experiences a closing or true fall, a trip, how do you proceed? Okay. As a construction engineer, you can have this experience during construction and energization, and you can have that experience right there, and during commissioning and startup. Okay, so this is how you answer it. Okay, first, I'll collaborate with my maintenance and operation personnel to obtain the first-hand information on the trip of the power transformer. And basically, believe me, those first-hand information is very, very important. You have a notebook. You write all the notes that you receive from the maintenance personnel, operation personnel, right? And any other person that might have seen or have any other information on how the transformer tripped, right? Okay. Then the next thing is to basically provide that indication to all your supervisors, managers, and basically provide them a path on how you're gonna proceed, right? Okay. Okay. So next is you obtain a single line, trade line drawing, schematics, wiring of the substation that the power transformer is located. Very, very important. Okay. Then you need to obtain the manufacturer's maintenance and operation drawings, right? And basically, the manuals. Very, very, very important. Okay. Then you need to obtain the maintenance history of the transformer, right? That's one of the most important documents. And also the operational history, right? Okay, so that is where you can talk to the operators, what they've seen, in the past, basically they have a log of all those things. So you go through that operational logbook to obtain any operational challenges that the transformer has encountered. Then next is that you want to collaborate, so that is when there's subject matter of expert for protection, because once a transformer, basically experience, that trip, right, protection comes into play, right? Other maintenance engineering discipline, high voltage engineer operations. Then you basically schedule a field visit, right, to basically perform inspection and data collection, right? Okay. So at the substation, right, then that is when you perform your visual inspection of the transformer. Very, very important, see if there's any leaks, right? Check all the gauges to see, what is the indication on it, Then go to the protected relay that protects the transformer, right? Okay, so you go to the 87. If you have a differential, you go to the 87T. You have a backup 5051. You have a 51G, right? Ground time over current. Then if you have a restricted head fault, right? 87N, right? Or this high impedance, the low impedance 60 for EF, right? Okay, so and the 51G, might be a backup for the 64 EF. Okay, so you go to all those relays to obtain information. If they've dropped our targets, basically obtain that information, the targets are there. Then most substations have a fault event recorder, right? Okay, so you go there to basically obtain all the waveforms and basically capture everything that you have in there. Then the next thing is you want to create a work order, a maintenance request, right? Okay, so that basically you can perform inspection, further inspections and oil sample collection and testing of the transformer. Very, very, very important. Okay. Then once you collect the oil samples, right? Okay, so when you're collecting the oil sample, you want to make sure that you obtain the top oil temperature at that time, winding temperature, humidity, then ambient temperature, right? Those are the information. Then also you want to avoid contamination when you are collecting the oil sample. So you're collecting the oil samples for oil quality analysis to be performed, right? Oil quality analysis, what am I looking for? I'm looking for oil breakdown for date testing, moisture, right? Acidity, neutralization number, furans, interfacial tension, right? If there are any metals, inside the transformer, oil. Then also DGA, right? DGA, I'm looking for all that string of gassing, right? Carbon monoxide, carbon dioxide, acetylene, C2H2, right? Ethylene, C2H4, methane, CH4. Methane is CH4, right? So all these gassing, right? Then hydrogen, right? H2, right? Okay, so all these gassing are what basically we are looking for. If there's any, excessive increase, so you collect all these, the oil to be sent to the lab to obtain that. Okay, then you schedule, right? To perform the testing on the transformer, right? Okay, so since based on the protected relay records, right, you've been able to substantiate, you've been able to validate that yes, indeed, the transformer experienced a through fault or closing fault, then you need to perform SFR testing, right? Because what the closing fault or the sweep the through fault does is basically it creates the fault current is so huge that it creates a huge electromagnetic force that basically moves, shakes the active component of the transformer, right, the core and coil. So basically, though the core and coil component, the active component, is bolted to the enclosures of the internal components of the main tank, right, and basically held in place. But at least the movement can basically that shaking can basically move the active component. So basically, you perform the sweep frequency response analysis testing to compare that fingerprint waveform with the baseline waveform that was obtained in the factory, during the factory acceptance testing. Or basically, if you've had a previous testing, then you can compare the results just to make sure that the active component is not damaged. And a lot of this testing you can move to that if based on the DGA testing. If the DGA testing is indicating high combustible gassing, then that is when you need to enforce that and perform the impedance testing in complement with that. Next is then what you do is basically once you receive the results for the oil quality analysis and the DGA, you have to review the results, right? Okay, then interpret the results, and what you have to do is don't rely on databases. I know that there are a lot of databases where basically you input the testing results are from the lab, and they basically review and spit out the results. What I would suggest is, as a discipline engineer, right? Okay, you review the results yourself, right? Then you compare it with basically what the database is saying. That itself, basically, it's more of helps you, as an engineer, to basically make your own analysis and not rely on database algorithms. Okay. Next, you review your electrical testing results, right? Okay, all the testing that is done, and we'll go through typical testing that is done during set. Then, basically, set up a meeting with with all stakeholders and collaborators, operations, maintenance, and engineering to discuss the results. And if all the results meet the criteria, and one thing is basically you also want to compare the electrical testing results and with the maintenance history results, or the last time the transformer was tested, just to see that if there's a significant change in the testing results. And basically that itself will decide upon the need to return the power transformer back to service. So that's how you answer that question, to get all the score points. Next, tell me about the typical routine testing that can be performed on power transformers. That's also another good question that can be asked. So for that, this is a list of typical routine testing, and this is done, anytime, let's say during time-based maintenance, scheduled time-based maintenance for a power transformer. That is every 6 years, right? Or let's say if the transformer basically, encounters a true fault or closing fault, then that is when you have to test the transformer to make sure that everything is okay with the transformer. So these are the list of testing that you can make mention, right? All these that are listed here. Next question is, tell me about the typical protection scheme for power transformers. And a very popular question that you can be asked. Okay, so this is how you answer this question. For a power transformer, typically 5 to 10 MVA and above, and based on the criticality of the transformer, right? Okay, typical protection for power transformers can be grouped into electrical side, electrical protection, and mechanical protection. So for electrical protection, the first protection is differential protection. That is ANSI device 87T, right? And this is the main protection scheme for power transformers. And one of the things that you want to add to this is the ANSI device designation number based on IEEE C37-.2, right? If you add that, basically that itself tells the interview that, okay, you know what you are talking about, right? These guys, because protective relays engineers talk up, utilize numbers as their language jargon, right? Okay, and in addition to that, you have backup protection on the high voltage side. For the backup protection, I have instantaneous, that is ANSI device 50, then time over current, that is ANSI device 51. And this backup protection, that is basically protects the high side of the power transformer if your main differential protection should fail. Next is magnetic inrush, right? Okay, so this protection scheme is implemented during energization of the transformer, where basically you have a huge magnetic inrush current from let's say 6 to all the way up to 6 times for smaller size transformers, and all the way up to 12 times for medium size, and for larger transformers you can get all the way up to about 30 times the full load current, right? Okay, so that itself, the transformer might misinterpret it as a fault current if you don't put in the right protection scheme that is going to distinguish between a magnetic inrush condition with a true fault, okay, with an actual fault, because the distinguishing factor is a magnetic inrush condition is rich in harmonics, has a high percentage of harmonics compared to true faults, right? Okay, so we utilize the second and the fourth harmonic content. So that itself tells you the reason why some customers ask for that as a special test to be done on the transformer, right? They use a power quality meter to measure the components, the percentage components of all these as part of the inrush current to be able to set the differential relay to inhibit the relay from operating based on the high percentage of a second and the fourth harmonic. Other than that, the relay will think that it is a fault condition and will trip, spuriously, right? Okay. Next is a drain over oxidation condition, right? Okay, so during energization, because the primary side is open, you can have an overexcitation condition, which can result in overvoltage condition. So basically, you want to utilize the third and the fifth harmonic content of the magnetic inrush to distinguish between a magnetic inrush condition and an actual fault condition that can result in an overvoltage condition or load rejection condition that can result in overvoltage condition. Next is a restricted air fault protection. For restricted air fault condition, we have two types. We have a high impedance restricted air fault condition, which is ANSI device 87, and low impedance restricted air fault, that is 64 year. Okay, so then you can further say that, okay, because the main differential protection, let's say for a delta Y transformer, right, Y ground transformer, because the main differential protection cannot see faults right at the neutral of the transformer or to the ground point, it becomes very challenging to have protection in this region, in this let's say 5 to 10%, right? Okay, so restricted air fault protection is added to complement the main differential protection. The restricted air fault protection is a very sensitive protection that protects the last percentage, 10% neutral of the low voltage winding. Next is a surge arrestor protection, right? Okay, for overvoltage condition due to lightning impulse and switching impulse, right? You install surge arresters on either the high side or the low side, or both. Next is if you have a transformer that is used for generator step application, right? Let's say you have a generation source, right? Then you have a transformer, and you have a utility system, right? The grid, right? You have a GSU, right? Okay. So volts per hertz protection is utilized, right? That will protect, the generator and the GSU step up, right, from overexcitation, which can result in overvoltage, and that is ANSI device 24, right? That is only for GSU application. So now let's talk about mechanical protection. The previous slide I made mention of electrical protection. I told you that for transformer protection we have the electrical protection and mechanical protection, and I did mention all the components of the electrical protection for power transformer. Now let's talk about the mechanical protection, right? Mechanical protection is implemented to complement the electrical protection, and we have the sudden pressure device, and I indicated to you that's ANSI device 63, right? It's basically the very sensitive protection that basically it even complements the protection action of differential protection, because sometimes very small 10 to 10 faults, right, strand fault, right, it might not be able to generate enough differential current change, right, for the differential relay to detect, right? Okay, so as such, the differential relay won't be able to operate, right? But it is the sudden pressure device that will basically detect this minute current through its pressure wave created from that. Next is a pressure relief device, okay, and indicate to you when it basically operates. Then oil temperature gauge basically providing temperature protection for the transformer oil. Then also winding temperature gauge protection, providing temperature protection for the transformer. Then oil level gauge, right? Basically it protects and make sure that the transformer oil level is within its set required criteria. Then the Buchholz relay, right, also protect the transformer from incipient fault. Typical example is a 10 to 10 fault strand, and basically broken strands, broken connections. That type, might not create enough differential current for the differential relay to see, right? So all these protective relays complement, the main differential protection. And for power transformers, 5 MVA and below, or 1 MVA and below, right? Those are basically distribution, very distribution level power transformers, right? Okay, so what they use is, because of cost, right? Okay, so they utilize fuse protection and current protection, and don't put in much sophisticated protection. Then, in addition to that, it might have an oil level gauge and oil temperature gauge. These are the most protection that they apply on these transformers that are like 1 MVA and below. Now, another question. Tell me about typical vulnerabilities considered in design differential protection, and how is that mitigated? Okay, so in designing differential protection, there are a lot of vulnerabilities and challenges, and you need to consider that as and you also need to know that as a protection engineer, and as a other discipline engineer, as a maintenance engineer, you need to know that. Okay, so first one is CT saturation for external flow fault. Okay, so the CT that you will select, right, shouldn't saturate if you have an external fault, right? Okay, so you have a transformer, you have the high voltage side, you have the low voltage side. So for a true fault that is external to the zone, to the protection zone, okay, the differential protection is looking for this internal side, okay, internal, not external, right? And if you have a low voltage, if you have a fault on the low voltage side, what is going to happen? It's going to be a huge true fault, right? And that huge true fault can saturate the CTs, right? So that is why you do all the analysis calculations to determine that the CT that you are selecting and designing should mitigate saturation and prevent saturation. Okay, so that is why accuracy class of the CT comes into play. Then the selected bearing in X to R ratio, right? It's very important. So those are some of the typical factors that you consider when you are selecting the CT to mitigate saturation for external true fault. Next is magnetic inrush selectivity, and that is very important. I went through that, utilizing the second and the fourth harmonic as a ratio of the fundamental current, and also the third and the fifth harmonics as a ratio of the fundamental. Next is compensation for the different CT configuration, right? Okay, so for the high voltage winding, right, and the low voltage winding, let's say if you have a delta that is here and a Y winding, right? Okay, so if you have a delta here and a Y here, if you don't change the configuration of the CT, right, the inputs to your differential relay, right, your differential relay will see different currents that is coming in here, and as such will trip. We'll see it as a fault, right? So that is when the compensation comes into place. Okay, so what they do is for solid state and electromechanical relays, what they do is on the delta side, the CTs are wound in a Y, and on the low voltage side, that is wound in a Y. I'm talking about the transformer winding, wound in Y. Then your CTs have to be wound in the delta, so that it cancels the phase shifts, right? Remember, there's a phase shift of 30 degrees, right, between the high voltage side and the low voltage side. As such, that reflects into the current that the differential relay sees. So you need to cancel that, and that's when the compensation comes into place. Next is accounting for the CT mismatch, right? And you do that through something they call a tap selection, right? Okay, so because you have a different CT ratios, the transformer has a different voltages, right? Okay, let's say if you have a 115 kV over here, right, and you have 34.5 kV right over here, right? Okay, because of the different voltages, right, you have different CT ratios, right? So that itself introduces, difference in current, that can cause circulating current, right? Okay, so that itself needs to be accounted, by basically normalizing, right? It's to reduce that error, right? And when the reduction is done, that error is accounted in the setting of the differential rating. So that itself, let's say if it is a 3 to 5%, that is accounted, on the minimum pickup operating point of the differential rating. So that's how you mitigate that challenge. Next question. What are the functions of the Buchholz protection and sudden pressure device? And this is how you answer that question. Okay, the Buchholz really, and in the previous slide, I showed you where the Buchholz really is applied. Its application. Right? Its application is in open conservative tanks, free breathing transformers, open conservative tank transformers, right? Okay, so if this is a conservator, and this is my main tank, right? In between the conservator tank and the main tank, there's something they call downcomer piping, right? The conservator tank is acting as a reservoir, right? Its goal is to replenish the depleted oil level that is in here, right? Okay. So in between the conservator tank and the main tank is this Buchholz relay. Okay. And these are the three functions of the Buchholz relay, right? The first one is the oil level in the main tank, right? So periodically, right, as the transformer operates, contracts, expand, oil contract, expand, right? Definitely, at a point in time, the oil level is going to go down, right? Okay. So as the oil level goes down, then the conservator tank is going to replenish the depleted oil level, right? And sometimes, if the transformer has been in operation for 20 years, 30 years, right? Based on its location, right? If it is in a very harsh environment, corrosive environment, and also due to degradation of basically the transformer seals, basically that interface all the mounting devices, auxiliary devices with the main tank, right? They will degrade. Now, you see that the oil will leak through all these joints, right? So the oil level is going to go down, right? Okay, so what it does is basically, detects that oil level that goes down, then it replenishes it. So as it replenishes, right, the oil level inside here is going to deplete. And if it depletes, you see a vacuum here. Then that's when the Buchholz relay detects that change in level. Okay. Then trips basically it will see it as a very, as you know, the oil level is very important, either alarm or trip. Next is if you have an incipient, right? Incipient means the evolving fault. That's the meaning of incipient. Growing fault, right? And you can have a growing fault due to a broken connection, broken sterns, 10 to 10 fault, right? So these connections, broken connections, basically creates an arcing, right? And that arcing creates a gassing, right? Due to acetylene, right? So that, and other gassing that can, basically due to degradation of insulation carbon dioxide, and also heating of insulation carbon monoxide, right? And also, PD activity, right? It is hydrogen, right? All these gases are basically, because they are lighter than oil, they rise up to the top, right? And into a chamber inside the Buchholz. Then periodically, the volume of the gas becomes heavy. Then basically it either alarms, through a switch, micro switch, basically, to provide a DCS or SCADA indication of that. Next is a through fault, right? Okay, so let's say if the transformer should encounter a through fault, right? What is going to happen, right? There's going to be a high pressure wave, great pressure wave. Okay, so due to the electrodynamic forces created from the short circuit time, right? Force is equal to I squared, right? I squared, and basically, based on the distance, right? I squared D, right? So that electrodynamic forces basically creates a pressure wave that will force the oil to flow backwards. So at the very lower section, it's a vein or a flap inside the Buchholz device. So that flap basically moves backwards. If the high pressure oil, impinges upon it, then basically it activates a micro switcher basically to trigger the transformer. Next is a sudden pressure relay. So the sudden pressure relay, like I told you, that they are mounted on the corners of the main tank, right? You have a main tank, they are mounted on the corners. You have a transformer filled with oil. So a through fault will create a pressure wave by electrodynamic forces that will impinge upon the bellows, right, and activate and basically to trigger the sudden pressure relay. Tripper the breaker and isolate the transformer. Okay, so the sudden pressure relay is a ANSI device 63. It's usually wired to a 63 auxiliary relay, right, called 63X, right? Remember, this is a mechanical device, right? A mechanical device that has inside it has a micro switch, which is an electrical, normally open, normally closed, and a common, right? Whichever section you use. Then this is basically wired to a lockout relay, right? 86 lockout. Then it trips a breaker, right? That protects isolated transformer. So basically, it's through a through fault and closing fault, and also, if you have a tentative fault or strand fault, broken connection fault, basically that the differential cannot see, then this when the sudden pressure relay activates. Next is tell me about the different condition monitoring that can be applied out to power transformers, and that's very important. As a discipline engineer, you should know. As a project engineer, you should know about during the project equipment selection phase. As a project engineer, you should know all the different condition monitoring, because it's all part of asset management, right? And you should know what needs to be installed on this transformer to be able to identify, and monitor real-time basis on basically the parameters, the condition parameters of the transformer as part of a condition-based maintenance, right? Okay, so this is how you answer that question. Okay, so for a power transformer, these are the three condition monitoring that can be installed, right? Okay, so you can have a DGA, right? Dissolved gas analysis, right? Okay, so that itself have different grades depending on the size of the transformer, depending on the criticality of the transformer, right? Okay, so you can have the 2 gas, the 5 gas, the 7 gas, and the 9 gas. Of later, I think is the 9 gas that is later. So yeah, if you want to apply 9 gas, then that should be bigger transformers with a bigger MVA, right? Okay, but most often, distribution level transformers are, lower MVA is 2 gas. Okay, so basically, in addition to these 2 gas, 5 gas, 7 gas, you have it's monitoring your moisture level, right? Okay, so what it does is, you install, we have different vendors that can install that, and basically it can be installed as part of the equipment selection manufacturing stage during the manufacturing of the transformer, or it can be added as an add-on during, if the transformer is already in service, you can add that one too, right? Okay, so what it does is basically it provides you real-time basis, right? The gassing concentration, the moisture concentration in the transformer, and this is basically sent to your DCS, your SCADA system, through an RT. Okay, so sometimes, some of these DGA devices basically, can drift. There's something they call drifting, right? Can provide a false indication of gassing, right? So anytime you receive an alarm from your SCADA system, your DCS system, right, or your local HMI system, right, what you want to do is collect another oil sample, right, and send it to an independent lab, right, for validation, right, to make sure that it is true, a true gassing situation that you are receiving. Okay. Next is OLTC, right, on-load tap changer. Remember, I made mention that this tap changer is installed on the low voltage side of it. Transformer winding to provide voltage regulation, change the voltage taps, and to provide the required adequate voltage that is needed by the load. So as the load changes, the load, let's say if you have an increasing load, right? Basically, voltage is going to go down. So that is when you need to adjust the taps of the low voltage winding to be able to provide the margin of load that is required by the load. On the other hand, if basically you have a load rejection, right, what is going to happen? Your voltage is going to go up. So that is when you need to adjust the load to stay within the tolerable band or criteria. Based on your bandwidth. It's basically works based on the bandwidth set for the voltage regulator. Next is and also it basically you have other monitoring that is in place. Is basically your motor current. It monitors the motor current, the motor torque, contacts, wear. Right. So these are typical measurements that the OLTC spits out on a real-time basis. Next is bushing current monitoring. Right. So this is installed on the bushing tap. Right. If you have a bushing that is here, there's a tap here. Right. And if you have the flange, so this is a ground plane. Right. Okay. So the tap is installed here. Right. And you have the monitoring device also installed here. So what the monitoring device is doing is it provides a measurement of the C1 capacitance, right? Okay, so you have a bushing, right? Okay, so you have the conductor, right? That is here. In between the conductor and this electrode that is inside the bushing, you have a capacitive layer, right? C1, and from the electrode to the flange, we have a C2 capacitance, another section, right? In between that, you have a power factor, right? A power factor. Okay, so this bushing for a condenser type oil impregnated paper bushing is filled with oil, right? Okay, so it forms a capacitance layer. So what bushing monitoring does is basically gives you real-time measurement of all these parameters: C1, power factor time delta, C2 capacitance, and power factor time delta. Then it provides a leakage current, right? Then it also provides leakage current converted into watt loss. Then it also provides the current and the voltage, right, measurements. Okay, so this is how you answer that question, and get all the points. Next, tell me about the different strategies that can be implemented, maintenance strategy on a power transformer. Okay, so typical, for a maintenance engineer, as a maintenance technician, as an operator, this is how you answer that question, right? Okay, so the first one is predictive maintenance, right? And don't just tell them predictive maintenance. What type of predictive maintenance can you implement on a power transformer? The first one is infrared thermography, right? Okay, so we have depending on the maintenance cycle, we have a yearly or a 6-month maintenance cycle that is implemented as part of the maintenance strategy and cycle, right? Where basically go to the field and perform a thermography scan to identify hotspots, right? Okay. Then based on that, you review the hotspot signatures to basically identify or basically implement the corrective actions, right? Okay. Next is DGA, oil analysis. That's another predictive maintenance. Actually, one of the best predictive maintenance to identify broken connections inside the transformer, other faults inside the transformer. First-time information. Okay. Next is time-based maintenance, right? Okay, so this is one of the maintenance strategies. About 60 to 70% of industries practice that. I'll say about 30% are shifting from time-based maintenance to condition-based maintenance. Okay, so this is for a power transformer. This is based on a 6-year cycle, right? Basically, where the transformer is de-energized and basically taken out of service, and basically you go with your maintenance crew and basically perform inspections, right, and perform testing, right, and routine testing is performed on the transformer. So the routine testing that are listed on the previous slides are typical testing that is performed, right? Okay, so this becomes part of your maintenance history test results. Okay, next is the corrective maintenance, right? Corrective maintenance can basically, if you have a day-to-day challenge on a power transformer, let's say you need to implement, you can, typical example is, let's say you have an oil gauge indication, oil temperature indication, winding temperature indication. If you have any other, auxiliary fan, a cooling fan, failure, that needs to be basically replaced. It's called corrective. Okay. Next is a condition monitoring, right? Because condition monitoring is what I explained to you, where you install condition monitoring devices on the bushing, on the main tank for oil analysis, DGA, and on the tap changer, right? To measure the motor current, contact wear, contact resistance, and basically the motor torque as well. Okay. Next is a condition based, right? Okay, so condition based is much more deeper, right? And basically it's based on your condition monitoring results, right? Which is basically providing on a real-time basis, right, through your SCADA system, what you're seeing on the screen, right? And based on your time-based maintenance, right? And based on your predictive maintenance results, infrared thermography and other GA results, right? Then based on that, you can extend your maintenance cycle for a power transformer, let's say from 6 years to 10 years or 12 years, right? Based on the condition, right? And that itself is more of a cost savings, basically, also reliability. You don't need to take a transformer out of service when you have to, right? If the condition is good, right? So basically, it's all basically labor savings cost, parts savings cost, right? All those costs, total cost, and also it's basically helps you to transfer your resources to other areas that you might need. Another type of maintenance strategy is reliability-centered maintenance, right? Okay, so reliability-centered maintenance is all these maintenance strategies that is optimized, right? Based on criticality of the transformer, where it is located, and the customers it is feeding. If it is feeding critical customers, and also based on its health and safety, right? Then environmental concern, right? Let's say if it should fail, what is it going to do? A lot of environmental spill, right? Okay. Then also it's a loss of revenue, right? And reliability. So all these factors are basically plugged in to basically implement a reliability-centered maintenance. Next question, tell me about how you proceed with oil analysis and diagnosis. And typical, very good question. And this is how. Yeah, it is one of the most important oil sample analysis. Oil sample, collect oil sample for oil physical and DGA quality, and very good. You basically determine the condition of your cellulose paper and the oil condition, right? Deteriorating condition, and also if you have any bad connections, right? And also hotspots inside the transformer, and any PD activity and arcing, right? Okay, so basically you do that basically for moisture content and oil breakdown and power factor, interfacial tension, Furan analysis, and DGA gas, right? Okay, so you do all this basically to diagnose all these problems with the power transformer, and basically it's the first line of information to provide any deterioration condition in the transformer. With that comes to the end of my presentation, and thank you so much for your listening. Yes, and this is part 1 of my presentation series with a type of typical questions usually expect on high voltage substation equipment. Very, very important. And look out for the next presentation, and you can see it from my YouTube channel. And if you like this presentation, don't forget to like it and subscribe to my YouTube channel. Thank you so much.